best.
Hopefully it's big.
That's right. Hopefully it's all good. All right. Today we are going to talk about electron configurations, and I'm going to experiment using OneNote and seeing how that works for us. Oh well, it starts by not working at all. Okay, I mean red pen 2mm. There we go. All right, so it's working great. All right, so question, Eliana?
Alright, can you make it bigger though, like, or is that as big as it gets?
Well, if I make it bigger, I don't have as much writing space. But we'll make it a little bigger. Now, hey, this first part you don't have to read. It's just a silly cartoon. It's kind of funny. It's the idea that we have quantum mechanics, and they're just talking like car mechanics. Well, if I ordered the part today, then we could probably get it. And yada yada. So that's just a silly cartoon. But that's okay. We need silly cartoons every once in a while. Looking for where I'm going to drag down. All right. Maybe I'm not. Yeah, roll and scroll. Hey, so we are going to talk today about electron configuration. And electron configuration, write this down as a topic for today.
The one red?
Yes. Is that easy enough to see? Yeah? Okay. Hey, Eliana, if you would prefer that center desk, that might be easier than being at an angle. It's up to you.
Okay.
All right? All right. So electron configuration. The electron configuration is the arrangement that says arrangement of electrons around an atom.
What's that word after arrangement?
The arrangement of electrons,
No.
E minus S.
No, it's not about arrangement though. What's that word after the A after the double R's?
ARRANGEMENT. MENT. Mm-hmm. The arrangement of electrons around an atom. All right. So the first model that really, I don't know if we would say that this one began our modern understanding, but it definitely was a key, is the Bohr model. Now, Bohr pictured, there were some things that were correct and some things that were not about his model. He pictured protons and neutrons in a nucleus. Okay, so if that's a nucleus with protons and neutrons, and then he pictured electrons around the outside in circles. But he also pictured them being in levels. Okay? And so what was correct about this and what was incorrect? It turns out that they do not, in fact, orbit in circles. Okay, so they do not orbit in circular patterns, but they do reside in energy levels. And so there are distinct energy levels where electrons reside. So when we talk about Bohr, he gets a check plus for levels, but he gets an X for the idea of circles. All right. So he was the first one to really key in on the idea that and explain that that electrons orbited the atom in particular energy levels, which we now know to be true. But he thought that they happened in circles like planets, and that is not correct. Okay? Feel good about that? All right, I'm going to move on, and I think as I move on, I'm going to move to a different color of pen, because I need variety. All right, so let's try the green and see how that works for us. Maybe we'll try the rainbow before it's all over. All right. So this was our first. This was our first idea of them being in levels, but then we transitioned to, yes, there are levels, but what those levels look like. Okay. So again, we still have a nucleus. So I'll just say N for nucleus. And then we have level 1, level 2, level 3, level 4. And within those levels there are sub-levels, but they're not circles. Okay? And so it's not necessarily planets orbiting the sun. It's a little more like bees buzzing around a hive. And that's what we saw up here. Oh, but I was wrong. They're more like bees around the hive.
Do we write the quantum mechanical?
So I'm going to tell you what to write about the quantum mechanical model.
Okay.
So here's what I would like you to write about the quantum mechanical model. I would like you to write that we really, if we were going to give credit to one person for this, it would probably be a gentleman named Schrödinger. And I'm not sure if there's another E in there or not, but that's how I'm going to write it today. Hey, Sean, good to see you. Come on in.
There's just a quantum mechanical model of Adam Schrödinger.
Well, no. Schrödinger was responsible for the development of the quantum mechanical model. And the quantum mechanical model, Schrödinger generated some mathematical equations that when they are solved, they tell us where the electrons are most likely to be found. Okay? They do not tell us where the electrons are. We do not know where the electrons are. But if we solve the Schrödinger equations, we know with 90% probability where they're most likely to be.
So just put Schrödinger's mathematical law can identify where the electrons are most likely to be found.
Yes, that sounds good. We are not going to solve these. We are not going to solve these laws and these equations. That likely involves a math beyond differential calculus. I don't even know what math you would have to solve the Schrödinger equations. But it's certainly more math than I have. So we're not gonna solve them, but I am going to show you some pictures of the solution later, and that actually will be helpful for us. All right?
Hold on, I have a question for you.
Yes.
Do you know what calculus is? I've heard that word a lot, but do you know what math it's for?
I do. Calculus is an amazingly useful.
It looks really complicated though when I see it though.
It kind of is. Everything's complicated until you know how it works, and then it's not. So let's see. First, yeah, there we go. So first level, second level. And what I'm going to say about that is that each level has sublevels called orbitals.
Do we write that?
Yeah, let's do. But I also want you to know that these are, even though I've drawn them as circular to represent the levels, they are not necessarily circular. All right. So each level has sublevels called orbitals, and those are not necessarily circular, but you do have a first level, a second level, all the way up to the 7th level. Okay? And part of why we know that there are 7 levels, or one way that you can remember that, if you look at the periodic table, there are 7 periods or rows. And you remember that each row represents the starting of a new energy level. Okay? So each row represents the starting of a new energy level, and there are 7 of those, and so there are 7 energy levels. And we'll talk later about the orbitals that are in each of those levels. Hey, we're feeling good about that so far? Any questions that we want to ask? Okay. Elise, do you need to move so that you can see well? Okay. If you decide that you want to move, any of the seats are open to you, okay? All right. So there we go. Let's talk just for a moment about the Heisenberg uncertainty principle. The only thing that I really would like for you to know about this is that you cannot know both the position and the momentum of an electron. Okay? So let's go back to our green. You cannot know both the position and the momentum of the electron.
So this is where Schrodinger's cat came from?
No, although Schrodinger's cat is a little bit a part of this same idea, but it's the idea that in order to find out where an electron is, you would have to use something to detect its presence, and the something you would use would actually be larger than the electron. And so you can't tell where it is, you can only tell where it was. Because once you find it, you've knocked it out of the way somewhere else. Okay? And so we don't know where it is. And someone said, but why would you want to know where it is? That's a good question. I don't know exactly. I can't think of a particular application. It's just sort of something that you would think we could understand, but that we don't. All right, let's move on.
Oh wait, I'm too busy writing that.
Oh, no, don't write the whole thing. Just write the part that I put the little asterisk by. All right. And my plan is to try to save this presentation and make it available in our Google Classroom. So that's my hope. Fingers crossed. All right. And if not, then like I said, I'm recording right now, and we'll try that. All right. So let's see. Energy level, the electron energy level, or the electron shell. This is what I wrote just a moment ago. The idea that let's see, I'm looking to see if there's an eraser. I know that there is somewhere. Oh, hey, maybe it's that one. There we go. So once again, the idea that there's a first energy level around the nucleus, and then a second energy level, and then a third, and then a fourth. And what's correct about this is that there are ever expanding energy levels. But again, they're not circular. Okay, so this is a little bit of a misrepresentation. But we represent things with models to help us grasp them. But all models break down at some point. All models become untrue at some point. Okay, because otherwise it wouldn't be a model; it would be the actual thing. All right, so just appreciate the model for what it helps you understand. And what I want you to understand about this is that we have distinct levels where the electrons are found. All right, and within those levels we have sub-levels called orbitals. All right, we'll get to that in a moment. Each level is symbolized by an N, and it denotes the distance from the nucleus. And that is known as the principal quantum number. So I want you to know that N is the principal quantum number, And that is also the number of the energy shell and corresponds to the number of the period on the periodic table. So N corresponds to the period on the periodic table. Okay. So if we come down to the fourth row on the periodic table, that will be filling in the fourth energy level.
I thought you must write in as the principal quantum number or something like that.
Say that again?
I thought you said you want to write in as the principal quantum number.
I do. So N is the principal quantum number, but it corresponds to which period on the periodic table you're filling in terms of energy level. So if N equals 1, then we would say the principal quantum number is 1, and that would be us filling in the first.
Can I spell corresponds?
That would be us filling in the first energy shell or energy level. CORR. ESPONDS. Good job.
With the periodic table?
The principal quantum number corresponds with the energy level or with the period on the periodic table. All right. Hey, here's what else I want you to see. Let's see that we can use the principal quantum number to figure out the number of electrons that can fit in an energy shell, okay, or an energy level, and that is equal to 2n squared. So for our first energy level,
can we write that example down?
So our first energy level is 2 times 1 squared, which if I take 1 and square it, then that's 1 and multiply by 2, and so I get 2. So my first energy level can only hold 2 electrons. All right? Now, what about my second energy level? 2 times 2 squared, which is equal to, see, 2 squared is 4 times 2, 8. Okay, so my second energy level can hold 8 electrons. All right, I'm running out of space just a little bit, so I'm going to come over here for third. So my third energy level then will be 2 times n, which is 3 squared. 3 squared is 9, times 2 is 18. And then let's try out this little pencil and see what that looks like. Ooh, that's difficult to read. We're done there. Let's see if we can change the color. Oh, let's have like an orange map pencil. And see what that does. Oh, yeah, that's not better.
I like it.
All right. Well, there you go. We'll just thicken it up a little. 2 times 4 squared, which is equal to, see, 4 squared is 16, times 2 is 32. Now, at this point, you're like, hey, Mr. Willis, go ahead and do 5, 6, and 7. No. Here's why. Energy levels 5, 6, and 7 actually are repeats of the fourth energy level. The levels don't get larger after 4. Okay? So energy levels 5, 6, and 7 are, 5, 6, and 7 are actually repeats of the fourth energy level. All right? All right. So that tells us a couple of things. So what we need to see from this slide is the idea of increasing energy levels, that they are distinct levels of energy, and that they hold different numbers of electrons. We'll talk about why in a minute. All right? Questions about that so far? No? Hey, you guys are doing great. All right, we are moving on. Let's see. Scroll. Let's see. No, it doesn't want to scroll. Let's go back to red. Oh, that's why. Okay. Now, let me tell you what we want to write about electron orbitals. An electron orbital is a region within an energy level where there is a probability of finding an electron. Okay? So that, I want you to write that. Okay? So the orbitals are what I've been calling sublevels. So these are the sublevels of the energy level. So within the first energy level, then there is a sublevel. Within the second energy level, then there are some sublevels. Within the third energy level, there are some sublevels. And those are called orbitals. And we're going to talk about those orbital shapes in just a minute, and the orbitals that exist in each energy level. Now, the orbitals are where the electrons actually reside, but again, we don't know exactly where. Mr. Willis, what do these orbitals look like, and how can I know? You can know by solving Schrodinger's equations. Fortunately, other smarter people than us have done that for us. Okay, so no worries, Madison. All right. And once you solve Schrodinger's equations, check this out. This is a visual. So I want you to imagine a three-dimensional axis. Okay, so we've got our x, we've got our y, we've got our z. Okay, x, y, z. And as you solve Schrodinger's equations, you will actually get a scatter plot in 3 dimensions around that axis. And for the s orbital, if I take that scatter plot and then wrap some paper or some magical mathematical aluminum foil around it, it's actually going to make this shape. And that spherical shape represents 90% of the solutions to Schrodinger's equation. And so there's a 90% probability that an orbital, or that an electron within the s orbital will be found inside that sphere. How we feel about that? You guys are either taking it all in, or you're just like, Mr. Willis, I just don't even care. All right, hey, I'm gonna say you look enthused. All right, so I'm gonna assume. One of you keeps rolling your eyes. I'm not gonna tell you who. Yeah. I know, it's okay. I'm teasing you. Hey, that's all right. I would roll my eyes at this too. Hey, you see that we've got, now they've laid it out horizontally. So there's an X and there's a Y, and then the Z they've done vertical. Doesn't matter. But you've got this little sphere. This is the shape of an s orbital, because for the s orbital, the solution to Schrodinger's equations, 90% of the solution falls within this shape. And so that's 90% likely where you're going to find the electron, or the electrons that are in the s orbital. Does that make sense? Questions about that? Hey, here's something else that I want to tell you. So this is the first orbital in each energy level.
S orbital changes with the first.
Let's write that an s orbital is a sphere, and let's write that it is the first orbital in each energy level. Oh, my goodness. I wonder why I don't have the ink to text availability, because I definitely feel like I need to circle this and click that so that it will make those into nice, neat letters. Sorry about that. All right. Hey, so our s orbital is a sphere. And all the orbitals, let's see, let me see if I told you this earlier. Okay. I'm going to go ahead and add something here. All orbitals can hold a maximum of 2 electrons. Whoops. Oh, didn't mean for that to happen at all. All right. Let's come back up here and click on the green pin again. All right, so all orbitals can hold a maximum of 2 electrons. So we see that our s orbital, well, it can hold 2 electrons. Ooh, our p orbital. Our p orbital actually has 3 lobes.
We can go back up and one finish writing.
All right.
There.
Let's see. We got that the s orbital is a sphere, and that the first orbital in each energy level is an s orbital. All right. So there we go. First orbital in each energy level is an s orbital. All right. So looking at our p orbital, the p orbital has 3 lobes, one in the x dimension, one in the y dimension, and one in the z dimension. Now, each one of those lobes can hold 2 electrons, which means a p orbital
So you want to write p orbital?
can hold a total of 6. Six electrons total.
So just put p orbital can hold 6 electrons total.
Yes, that is a fine thing to put. All right, so the p orbital can hold 6 electrons total. And again, you see that they are kind of dumbbell shaped. That does not mean that the electron orbits in a figure 8. That means that 90% of the solutions to Schrodinger's equation for the p orbital belong in one of those 3 dumbbells. Okay? And so Madison, for any given, for any set of electrons, for any electron that's in the p orbital, there's a 90% chance that it will be within these dumbbells. Okay? There you go. Ooh, something else I want you to see is that p orbitals are in each energy level above n equals 1. So these start with the second principal energy level. Okay? So Andrew, first energy level, no p orbital, s only. Second energy level, s orbital, p orbital. So Andrew, how many electrons can I get into my s orbital? That's right, because two electrons, because that's all any orbital can hold. All right. Now, in my second energy level, my s can hold 2. And then I've got a p orbital with 3 lobes. Each lobe can hold 2, which means that p orbital can hold a total of 6. 6 in the p, 2 in the s, for a grand total of 8. And so that's where we get the idea from earlier that when n equals 2, the electrons that it can hold is going to be 8. All right? Hey, I'm going to erase that just because we said it earlier and because out of context that wouldn't make very much sense. All right, so you heard what I said, and I said what I said. All right? Good. We're moving on. Hey, so we're not going to say much about the d orbital. The d orbital is next. Where did these names come from? Don't worry about it. Mr. Willis, what does the S mean? Don't worry about it. Does it stand for sphere? No. Okay. Don't worry about the S. The S holds 2 electrons. The P has 3 lobes, so it holds 6 electrons. The D, ready for this, has 5 lobes at 2, okay, so 5 lobes at 2 electrons each. So how many can my d orbital hold? 10.
Do you write all that?
Yeah. Okay, not all of this. Let's write the d orbital shape has 5 lobes. Each one can hold 2 electrons for a total of 10 electrons. And I want you to put that they begin with n equals 3. Oh, that's terrible. I just drew a line through that. I meant to underline.
That's 5 lobes, and what else?
5 lobes at 2 electrons each, which means it can hold a total of 10. Okay. And so we've got one that looks like a set of dumbbells or a set of eggs, 2, 3, 4, and then the 5th one is kind of a dumbbell with a donut. So the math is really getting crazy at this point.
They can hold what? They can hold which they can hold 2 electrons, which means they can hold what again?
Hey, watch my hands. There are 5 lobes that hold 2 electrons each, which means
They can hold
10 total. All right, and that's where we are with that. And remember that they do not show up until so energy shell number 1 only has an S. Energy shell number 2 has an S and a P. Ooh, but energy level number 3 has an S and a P and a D, which means it can hold up to 2 plus 6 is 8 plus 10 is 18. Ooh, cool. Huh?
The 4th energy level have a special one too.
What do you mean by a special
It's
one?
like another shape.
Oh, dude, the 4th energy level, the shapes are... This is the first presentation that I've seen where they actually try to show you the F shapes. Usually they just say, don't worry about what shape the Fs are. Okay? So you ready for this? Ready to blow your mind? Wow. Uh-huh. What? And so, hey, just say to yourself, oh, look, that's the 3-dimensional representation of Schrodinger's equations for the F orbitals. And just leave it at that. It looks like kind of some raindrops in a funny arrangement. Hey, here's what we need to know. Here is the important stuff. we need to know that the f orbital has 1, 2, 3, 4, 5, 6, 7 lobes. At 2 electrons each, for a total of 2 times 7, 14. Hey, and, tell me?
The F orbital has 2 lobes, and what else do I need, right?
7 lobes.
Oh, sorry.
And can hold 2 electrons each, like all orbitals can.
And can hold 2 each.
Hey, guess which level these start showing up on? Try again.
First.
Beginning at n equals, you're a terrible guesser, n equals 4.
Okay, so what else? It has 7 lobes, can hold 2 electrons each, and what else do I need, right?
I want you to write that it begins, that we begin having f orbitals at n equals 4. Which means that n equals 4, we have S, P, D, and F for a grand total of 2 plus 6 plus 10 plus 14 for a grand total of 32 electrons. All right. Hey, we feel good about that? All right.
So after we're about F orbitals this time?
We will worry about f orbitals anytime that we're on the fourth shell or higher. Okay? Hey, we'll talk about how they fill up in just a minute, okay? All right. So let's move along. All right. Ooh, this is going to be a very helpful page for you. Oh man. On the PowerPoint, when I click at these things, the yellow goes away, but I'm afraid that we're probably stuck.
Get purple so I can make it pop out more or something.
You know what? I like it. We haven't used purple yet. Let's do purple, by all means. All right. So let's see. Let's trade in the red for purple. Let's try Panther. That's not indigo. That's purple.
You can make a new. Can you like make new colors though? Like you can
I could, but I'm gonna stick with this. Hey, in energy level 1, the only thing that we have is s orbitals.
Do you write this down? Or?
Yeah, we need to write this down. This is a nice little summary page. I want you to write this down.
Do you have a chart that we can write down?
Well, we're making the chart.
Okay.
Hey, this will be in our Google Classroom, we'll work it out later.
Okay.
Okay? Hey, so the orbital type within energy level 1, there's an S. An S only has 1 orbital. Okay? Now, 1 orbital, any orbital can hold how many electrons max? That's right, 2. Okay? Which means the number of electrons in that energy level is 2. Now, second energy level, we have an S and we have a P. Now, the total number of orbitals, it's 1 and 3, but the total number of orbitals is 4. Okay, 1 for the S, 3 for the P. Because you remember that P had 3 lobes. So we got 4 orbitals. Now wait, if each orbital can hold 2 electrons, what's my maximum number of electrons? 8. that should end up being over here. Okay, so I'm clearly filling in something slightly incorrectly. Number of electrons per energy level. Yeah, yeah, that should be that. So I'm not sure what should go in the number of electrons section. Okay. We're moving on. Question,
I was
Eliana?
wondering if you could like print me out like a copy of this thing though.
We'll figure it out. Okay. All right. Hey, third energy level. We've got an S, we've got a P, and we've got a D. Okay. The S has the S has 2. I tell you what, we're going to write it this way. The P has 6. The D has 10. All right. And then that's going to total up to be 18. So that means I need to come back and adjust this to. Okay. All right. Let's see. So check this out. So the S and the P, there's 1 S orbital and 3 P orbitals for a grand total of 2 and 6 electrons for a total of 8. Okay. Whew. I don't know if this is going to be better or not. So the S, there's 1 orbital. The P has 3. The D has 5 for a grand total of 2, 6, and 10 for a total of 18. Now let me write this one this way. S, P, D, F. The S only has 1 orbital. The P has 3 orbitals. The D has 5 orbitals. And the F has 7 orbitals. Now, if you've only got 1 orbital, you can take 2 electrons. If you've got 3, you can take 6. If you've got 5, you can take 10. And if you've got 7, you can take 14. And all of that adds up to a whopping 32. And what I want you to know is 5, 6, and 7 are repeats of 4.
Let's see if I take a picture of this thing so I don't.
Go ahead. All right. Now, hey, what questions do we have about that so far? You guys have been very non-full of questions. Madison, how you feeling?
Well, I'm confused about how this dude, okay, so when was this dude, like, alive and making all these equations?
Okay. So Schrodinger was generating these equations in the early 1900s, so the early 20th century, so about 100 years ago.
And how did he come up with these equations and, like...
That I can't tell you. How did he come up with these equations? I do not know. Some of the reasoning and the reasoning and the mathematics that go into this is beyond me, and I'm way impressed with how this, and of course this is why they give out Nobel Prizes to people like him, so it's crazy.
Did he have, like, any way to, like, check if all of this was, like, true, like, even, like, the...
Yeah, I understand what you're saying. How do we know this is true? Here's what I'll tell you. Number one, we understand that things are true if they offer predictions for natural observations and phenomenon, and if those are then found to be correct. And so if they predict correct behavior, if they describe already observed behavior and can predict yet unobserved behavior that then when it's observed becomes, is found to be correct, if it's both descriptive and predictive, that really lends a lot of credibility to it. And that was the case. That's why nobody wins a Nobel Prize the year they make the discovery. Usually you win a Nobel Prize like 20 years later after you publish your paper. Because it takes that long for your record-breaking, groundbreaking findings to be verified and for people to realize, wow, that really was a big deal and really was an amazing, new understanding of our universe. And so you don't win a Nobel Prize the year that you publish the paper, you win it 20 years later. And hopefully you're still alive because they don't give Nobel Prizes to people who are dead. And so if you die, then they give it to somebody else and say, wow, that was amazing what that guy did or what that lady did. But you don't win the Nobel Prize if you've already passed away. Very recently, there was actually a case where 3 people had worked on the Nobel Prize together, and 3 people had worked on a project together. One of them passed away, and then the Nobel Prize was awarded to that project. So the other 2 received the Nobel Prize, and the third guy is just known as the other guy in the group, but did not actually receive a Nobel Prize because they will not award them posthumously. So. I know. I think that they may have, in that case, actually awarded it to his estate, and given him. But I can't remember. I can't remember if he got credit or if he did not technically win the Nobel Prize because he was not alive. So there you go. Hey, I know. I mean, hey, here's the deal. You gotta make your discoveries while you're young so that you can get them verified and get your cred. Okay, that's true. Only the good die young, so just don't die. So what have we learned? Vampires win Nobel Prizes. Okay, there you go.
And something that makes you live forever.
Or you could discover the fountain of youth, get the Nobel Prize for it, and win it every year because you're the only one who lives long enough. All right, hey, we're moving on. All right. So orbital, here's what I want you guys to see about how, I want you to look at get your periodic table out and look at it, okay? And I want you to see how the orbitals fill. All right? And the orbitals are actually going to fill across, let's see, I think I'm going to replace the green this time. I think I'm going to replace it with a nice, that is not purple. I think we're going to replace it with a plum. All right. Hey, and here's, rainbow. It's very tempting, but I want us to be able to follow this. Hey, here's what I want us to see. As we begin putting electrons into shells, the first shell, okay, remember energy level 1, only has an S. Okay? And that S, so level 1, orbital S, and then at first it gets 1 electron, and then it gets a second electron. So we describe that as 1s2. Meaning that we have, energy level 1, orbital S, and when it's full it has 2 electrons. Now, the next one, level 2, has an S and a P. So we will fill first the 2s level, which can hold 2, and then we will fill the 2p level, which can hold 6. So 1s2, 2s2, 2p6. Then you'll notice that we're moving down to the third level on the periodic table. Well, we've got our s orbital, 3s2, and our p orbital, 3p6, and I'm just going to write it down here. And then here's the deal. You remember that we were supposed to have a d orbital also. Here's where it gets a little tricky. All right? Jessica, it turns out that the d orbital doesn't fill immediately. Okay? Because the third level is so crowded with the s and p that it's easier for the electrons to move on out to the fourth level than to keep trying to cram into the third level.
Do you write all that stuff down on the periodic table?
You don't have to. No, definitely don't write it on your periodic table. I just want you to look at your periodic table and see how, as it goes across, you can see how it would fill in. Okay? So Jessica, it's not going to fill in the 3D yet, because remember how electrons repel each other. And so it actually takes less energy and takes less effort for the 4s level. So we come on down to the fourth period and fill in 4s. Before we fill in 3d. Okay? So after we fill in 4s, then we start filling in 3d. So we fill in 4s around the outside. Then we go into 3d and fill it up. And it can hold up to 10. And then we go back out to the fourth level and fill in 4p6. All right? We feel good about that? Hey, it just keeps following the trend. And so this block, I tell you what, I'm gonna show you something different in just a second. But then we go to level 5, we fill in our S block, then we fill in our 4D, and then we fill in our 5P. When we get to the 6th, we fill in our 6S. Oh, but then you remember that we actually had, way back at level 4, we were supposed to start getting some Fs. That fourth level is so crowded. Okay, Andrew, that fourth level is super crowded. You can't be putting any more electrons in there until, we got to already be starting the 6th level before those electrons are going to go back and fill in this 4F. And then 5D, and then 6P, and then 7S, 5F, 6D, and then 7P. Okay?
What would ever happen if, I remember that you said that, like, how it's looking right now, that just won't keep going and stop under radon. So that doesn't stop under radon, then what exactly would happen with all of this?
That, Diego, is your Nobel Prize ready to happen. Okay? What would happen if it went past 118? Because right now we have no evidence that past 118 exists.
Question though.
Uh-huh.
How come on there, why is the lithium, or I guess that one has star behind it, how come that one and the one below it has 2 stars? Like, what do the stars mean?
I'll show you in a minute, but it means that they fit in right up there on next to, they fit in up there. All right, so I'll show you that in a minute. All right, hey, let's scroll down just a little bit. All right, here's what I want you guys to see. You can look at your periodic table and see how this is going to work. 1s goes all the way across, and we fill in 1, 2. Then we've got our S block. Okay, and so a lot of people, I'm gonna erase this and do a little more I like how well this erases. This is cool. Wow, that was efficient. Okay, I know. Wow. Very satisfying. We're going to go for some yellow highlighting here. Okay. And let's just max it out. Okay. Oh, what?
I think it's more.
Oh, okay. I got to go across. You're killing me on this.
I would try red.
Yeah, it blends in kind of.
Blends in too much? All right.
I would try red.
All right. Everybody's a critic. There we go. Okay. All right. So we're gonna try kind of something a little more pinkish, a little more crimson maybe.
I thought red would be good since red is green complementary color, so make it pop out more.
Okay. I like your plan. Hey, this is what we call. You asked for red, okay? So pipe down and enjoy it. All right, there it is.
Crimson, it's not red.
Hey, shh. Okay. Hey, there it is. This is the S. Oh. This is the S block. Okay. Hey, this is the P block. This is the D block. And this is the F block. Okay? And so as you look at those, you can see what shells will be filling as you go across. Hey, and we can pretend that helium fits right in here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Okay? And it just continues that way. Let's see. We are running out of time, but I want to scroll down just a little further. Why will this not scroll down? There we go. Okay, so two things that I want to tell you.
Do you have to write down?
Sort of. Okay. First thing I want to tell you about electron spin. I do not care that you write plus 1/2 and minus 1/2. Okay. What I want you to know is that there are two possibilities for electron spin. Sometimes these are referred to as up and down. Okay, I'm not going to ask you to learn the plus 1/2 and the minus 1/2. Here's what I want you to know. That represents the direction of spin of an electron and the magnetic field that it creates.
So what is it for electron spin?
Here's what I want you to put for electron spin. Within each orbital, remember that each orbital can hold a maximum of 2. Within each orbital, each electron must have a different spin. Okay? Within each orbital, each electron must have an opposite spin. So within our, for example, our 1s orbital, remember that we're going to have 2 electrons max. One is going to have an up spin and one is going to have a down spin, or plus 1/2 and minus 1/2. Within our 2s, we're going to have, again, an up and a down. Within our 2p, we actually have 3 lobes, so we have 3 orbitals. And what we'll find out tomorrow is that they actually fill up, up, up.
Is that supposed to be an is or 1s?
That's a 1s. And then down, down, down. All right? Let's see. Hang on, we still got 4 minutes, 4 good minutes. Ooh, this is called the Pauli exclusion principle.
2p up there, like 2p.
Wolfgang Pauli. Any two electrons occupying the same orbital must have opposite spins. Okay, big deal. And we will pick up there tomorrow. Okay, thanks so much.